Hello, this is Huayi Li. I'm a PhD student at the University of Michigan Ann Arbor. I'm co-advised by Professor Leah Komnovsky and Professor Anouk Gerard. The title of our paper is Integrating Failure Detection and Isolation into a Reference Governor-Based Reconfiguration Strategy for Stuck Actuators. Maintaining the safe operation of system is critical for applications such as spacecraft, aircraft, and autonomous vehicles. On September 8, 1994, U.S. Air Flight 427 crash ran its approaching the runway for landing, killing all 132 people on board. The investigation concludes that the accident is caused by a jam rudder. On July 29 last year, a spacecraft module docked to the International Space Station accidentally fired its thruster continuously, causing the space station lost altitude control for more than an hour. In just 3 months on October 15, a similar incident occurred for the second time. Luckily, the crew and the space station were never in danger. In the automotive domain, car companies are developing systems with backups to avoid car accidents caused by component failures. The takeaway here is that safe operation is extremely critical in many industrial applications, despite the potential occurrence of failures. There exist many studies on fault-tolerant control with the focus on various aspects including FDI and failure mode reconfiguration. Specifically, there are strategies that consider different features such as constraint satisfactions and reference checking. And based on the location of the failures, some studies focus on stuck actuator in particular. To draw a conclusion of the literature review, we observe that there's need to develop a systematic approach that can simultaneously include all these highlighted features. In addition, the approach should guarantee the safety of the system at any time, guarantee the isolatability and reconfigurability, have finite duration for isolation and reconfiguration, and lastly, be able to handle sequential failures. To close these gaps, we propose a set membership-based and reference governor-centric strategy. In our previous papers, we have successfully applied the strategy to handle failure mode reconfiguration, but without considering input disturbance. In the current ACC paper, we extend the strategy to include failure detection and isolation, with the addition to include set-bounded input disturbance. To specify the scopes, we consider systems with actuator redundancy, stuck jam actuators, and set-bounded unmeasured disturbance. Our goal is that in case of a failure, the system should maintain a safe operation. At the same time, we should be able to isolate the failure and reconfigure the system so that in the new operating mode, another failure cannot lead to safety hazards. Meanwhile, the system availability should be maximized. More specifically, the problem is to design an FMEM strategy to handle failures that lead to transition of operating mode and the sequential events caused by such failures. The strategy should guarantee safe operation at any time while performing reference checking. The major assumption includes that only one failure can happen at a time. There is sufficient time between sequential failures for the isolation and reconfiguration, and we can acquire the exact state measurements or estimations. Before we move on to the details, here's the high-level summary of our strategy. The online operation includes 3 phases where a reference governor is used to check reference. All modified reference as well as the isolation and reconfiguration sequence are generated by solving quadratic programming problems. So to guarantee the feasibility of these constraint optimization problems, an offline design based on set membership condition is done before the online operation. In the following slides, we'll see the development of this approach. I'll first introduce the mode-dependent dynamics and constraint for the type of system that we consider. And then we'll see the setup of the online operation and the conditions for isolation and reconfiguration that need to be designed offline. A mass spring damper example will be shown at the end with some conclusion remarks. We consider systems with n actuators. M is the mode from 0 to omega. An example of all possible failure scenarios for n equal to 2 is shown on the right, and the closed-loop system is shown at the bottom. U is the open-loop input, mu denotes the working input, and D denotes the failed input. The open-loop dynamics are represented by equation 1 to 4, and the reachable set is shown by equation 5, where U star is the sequence of input commands. Stabilizing controllers can be designed to command the working input mu. Equation 6 represents the closed-loop system dynamics, where the closed-loop input UMK contains elements of the modified reference VK and the failed actuator position DM. The sets of point-wise in-time state and control constraints are given in equation 7 by a set of inequalities, shown by the solid black ray in the figure. Modifications to these constraints are considered to facilitate the subsequent design of our FMEM approach. The tightened and relaxed constraints are to be designed as defined by equation 8 and 9, and they are shown by the purple and orange ring in the figure. Before further discussion of the strategy, we first need to define the constraint admissible set. The constraint admissible set is a set of constant closed-loop input UM and initial states x0 such that the constraints are satisfied for all future time. The constraint admissible set defined in the form of equation 10 has two nice properties. It is finally determined as given by equation 11, and it is also invariant. Here's the framework for the safe online operation. We'll begin from phase 0, where the system is running in a certain mode. A reference governor is run at every time step by solving this QP problem using the constraint admissible set to provide a modified reference for safe reference tracking. The failure detection is also run at every time step. If the state is outside the expected reachable set, then the failure is detected. The system operation will switch to phase 1, where an isolation sequence will be generated by solving this MIQP problem. The idea is to use this input sequence to steer the states into sets with empty intersection for different modes. When the system finished running with the isolation sequence, it moves on to phase 2, where a recovery sequence is generated by solving a QP problem. The system will run with the sequence until the reconfiguration is finished, and then it returns to phase 0 and starts operating in the new mode. To ensure the feasibility of these QP problems, we need an offline design such that the states at the end of each phase should be already inside the feasible set of the successor phase. So we define the isolation and reconfiguration conditions accordingly, but before that, we need to define some sets that are related to the conditions. Firstly, we denote the set of states upon failure detection as IM0. The isolation set is the state projection of CM0, which is the feasible set for the MIQP problem that generates the isolation sequence. For the reconfiguration, we define the set SM0 as the set of states at the end of the isolation. And the intersection of R infinity M is the recoverable set. The R infinity set is a set of initial states x0 such that there exists a recovery sequence V0 to Vnm to steer the states into the state projection of O infinity M within a certain number of steps Nm, while satisfying the safety constraints XRM during the recovery. To guarantee the feasibility of isolation, we need that the set of states upon failure detection is a subset of the isolatable set. And to guarantee the feasibility of system reconfiguration, we need that the isolation condition holds and the set of states at the end of the isolation be a subset of the recoverable set. Three mechanisms can be used to satisfy these conditions. We can tighten the constraint of the preceding mode, and we can also relax constraint and allow more steps for the isolation and reconfiguration. Now let's apply our methods to a numerical example considering a mass spring damper system. The dynamics, constraint, and definition of modes are shown on this page. The system has two redundant forces acting on the mass and is trying to check the given displacement. The offline design goes backward beginning from mode 3 where both actuators have failed and end with mode 0 which is the normal mode. The length of the isolation and reconfiguration sequence are set appropriately and the mechanisms to tighten and relax constraints are used to satisfy the conditions. The simulation results show that there is no constraint violation at any time during the operation and the displacement is tracking the modified reference command. To summarize, we consider systems with stock actuators and set-bounded unmeasured disturbance. A set membership-based and reference governor-centric approach is proposed to achieve systematic failure mode and effect management. And we show our control development using the study case of a max spring damper system. The proposed strategy has guaranteed safety, ability, and time duration for isolation and reconfiguration, as well as the feature of reference tracking. There are many possible directions to be considered in the next steps. Here, I'm highlighting a few that have practical importance. Firstly, we should consider other types of failures in addition to the current stock actuator failures, such as the ones that slowly change with bounded rates. Another example is failures caused by sensor and communication malfunctions. Secondly, we should consider challenges when implementing the strategy in real time. For example, we may need a backup plan when the isolation and reconfiguration sequence cannot be generated in time for the online execution. In closing, we hope this presentation could give you a quick overview of our set theoretic approach to fault-tolerant control. For more details of the strategy, please refer to our paper. Thank you very much, and I'll be happy to take your questions.